All right. Well, thanks everyone for coming. I'm Mike Feenan, and this is Katie Markovich joining. Will be your instructors for the Americas edition of the GMDSI tutorials. And if you attended the overview a while ago, you saw our painful introductory videos. It was very hard to do, like in the abstract. But yeah, we're just going to jump right in. And so we'll be trading off kind of who's presenting and discussing things a little bit, and just a couple kind of background ideas or thoughts. I think it'll just be easiest if everyone can just stay muted. We'll have opportunities for discussion, especially in the later sections, maybe less in this particular. Today's a little bit more one way, but we do hope that there will be some lively discussions. We're going to try to make it as orderly as possible. There's a lot of us, so if you can use the hand raising facility that's at the top, that will be great. And feel free to at any time type things into the chat. Whichever of us is not presenting, we'll do our best to keep our eyes on that as well. And then when we get to discussion places, you'll have the opportunity to unmute and discuss things. So that'll be cool. Another thing is on the GitHub site where you all got the materials in the first place. Actually, I'm going to share my screen here real quick. Yeah, there we go. So on the GitHub site at the top, actually, if we go just to the GMDSI notebooks site that you all should have seen at some point, you'll find this discussions section, and this is a great place to post to start discussions, and that way, everybody who's participating in this, all the other students and the people that are instructing, our colleagues in Australia and New Zealand, will be able to participate in the discussions as well. We'll all try to keep our eyes on this. A couple real advantages to this are that they're available to other people generally that are in the class, but also they're going to be available, like it's a little bit more Googleable. Like if people are searching for some of the keywords that turn up in some of these discussions, it's likely that people will actually find these materials online, which is really cool. It kind of helps make the community be able to discuss things in a larger sense among all of us, and we think that can be really useful. So encourage you to use that. But of course, like as we're discussing things more actively in the class, we'll the hand raising and chat will be good. And so basically these, we put together these tutorials, and there's a whole sequence of tutorial notebooks in the tutorials folder here. And the idea is really, you can basically run all of these. You open it up, and if you just hit shift and enter over and over again, you'll step through each cell block. Some of them are just descriptions, and some of them are actually running code. And you'll run through the whole sequence of problems, which is cool. But if you just kind of shift enter and smack your way through really quickly, you're not going to retain very much. And so the design of this course is that we've added a lot of discussion materials in these notebooks that hopefully give some background and interpretation and context. And we're encouraging people to really spend time and think through things. Feel free to change stuff. To change things along the way if you want to, and experiment, because really, the way that you deeply learn this stuff is through failure. It's through trying things, failing, trying again, figuring it out. It's the dead ends and challenges that actually are where those are the things that help us reinforce and learn how to do it right and how to get things working. So at the end of today, we'll kind of give you your first assignment for next week. And the idea will be everyone can work through those notebooks to the best of your ability. If you get stuck, the discussions are a great place to go. And if you, right, and then we'll have an opportunity to sort of discuss as a group what we all saw and learned the previous week. We'll give you a little bit of information for the next topic, and then you'll move on from there. So that's sort of the design. It's really, you know, learn by doing, or maybe learn by struggling or failing. You know, that's I think how all of this can get deeply understood for all of us. So one thing wanted to kind of cover as an introductory topic is, you know, the way that we're distributing the materials for this class is through Git. And Git is basically like a software versioning tool that's really useful. And it's designed for code, but code is just files at the end of the day. And so some of the really powerful tools within Git, in terms of allowing people to share materials and all have like the same definitive version of things, that everyone's working off of the same page, in a sense. That applies to models too, or scripts that support models, which is an approach that we really are all kind of proponents of. So we wanted to give you just a quick kind of overview of how you can use Git, and how we kind of use it in our modeling framework as well. And so to do this, we'll just do a quick little demonstration. I went out to GitHub and just created a random empty repository here. And they give you these lovely little sample names. So Reimagined Adventure is the name of this repository. And so if you go to the code button and copy the address here, you can go into a command line. If you're on Windows, this would often be through something called git bash, or on like a Mac or Linux, you just do this through the terminal. And if you just say git clone and then copy and paste that address, it'll say that it's cloning into this thing. And now if we look at in our in our folder, we'll actually have a new folder called with the name of the repository. So in this case, Reimagined Adventure. Hopefully you all basically did this to get the GMDSI notebooks in the first place. You might have gone to a different link where you just download a zip file, which is totally fine for that purpose. But if you want it to be interactive, you have to do this cloning thing. And so if I just change directory into here, the only thing that's in there right now is a README file. And if we look at all the hidden files, there's actually a hidden folder called .git that's going to create a database of changes to files, which sounds a little bit crazy, but the basic idea is that every file that Git is tracking, or that you make Git aware of, Git has the ability to then track any changes to it. So it doesn't make new copies of the files every time there's a change. It keeps track of just what's updated in a file. So then it can reconstruct the state of those files anywhere along the way, which is really powerful. And so, so for example, if we wanted to make a repository now with our model files, let's just take, I'm just going to go into that directory here. Was it Reimagined Adventure? Yeah. And then, we can copy, say, from the GMDSI notebooks, one of the models that already exists. So I'll just go to grab one here. Oops. Yeah, from the pest setup folder. We can just, whatever, it doesn't matter. We'll just grab this one. All right. So now if we look in this directory, we've got this whole folder called Freiburg Pest Setup Files. And if we look what's in there, it has actually, okay, in this case, it just has some files, some pictures. That's fine. So if we say git status, that's the way to see what Git is tracking. And it actually isn't tracking anything new, but it does say that there are untracked files in here. So we can add these with the git add command. And then if we say git status, we'll see that there are new files in here. So, and if we go into that directory, and we can just make a new file too. So this will be fancy model file.dat. And we can say this is a file. Very exciting. So now we've got, if we say git status, again, we'll see we've got those new files, but now we've got another untracked file that we didn't have before. So I can add that one. And then if we do status again, we see that it's added. So this is just telling Git what to keep track of. That's all we've done so far. If we want to then send these files out to GitHub so that they're available for other people, we would have to make a commit message. So git commit, and we would say new files added. Hopefully these messages are something meaningful, like I made a change to the recharge package and something like that. In reality, a lot of times they end up being an end of day or something like that. But if we look now at the log of what Git is aware of, we can see that this message shows up. So as your project progresses, you can start to have more and more states, like more and more changes that you could back up to. All right. So then so Git is basically the software. It's running on everybody's computer. But if you want to, everybody who's on this project, but GitHub is one of a few options, probably the most popular one, where you can host this stuff in the cloud. And so what I'm going to do is reconcile my changes with what's in the cloud by saying git pull, and it tells me everything's up to date. But if I say git push, it's going to push my changes up to GitHub where we started this whole process. So I guess one of those files is a little bit big, so it's going to take a second. All right, cool. So now if we go here and refresh the page at GitHub, we're going to see that folder showed up, and all the files that I just added are in there. So I know that was a super whirlwind, but the idea here is just to show that we can now have this definitive set of files that anyone else can interact with. So as an example, Katie's going to show how she can pull this down and then make either a change or add something to it and reconcile it back to here. So I'll turn it over to you, Katie.
Yeah, sure thing. Yeah, so we use these in our workflows. We use Git in our workflows because it allows sort of like collaborative and almost near real time working on a modeling project, which, if you're working in, say OneDrive, which is like maybe the next best thing in terms of having some kind of rudimentary version control, even then you can run into versioning issues, right? So if everybody is pulling and pushing appropriately to the GitHub and tracking everything, it helps, I think, reconcile those divergences that are going to happen just even day to day. So one way that I can work with Mike on this project is if I was just another, say, co-owner of it, which hopefully I'm able to push to it, Mike. So this is, I just go to github.com, go to Mike's profile, and let's go to, here's Reimagined Adventure. So from here, I can do the same thing Mike just went through and clone it to my desktop and, make a change to a file and push it, the same process. But let's say, Mike is a awesome USGS developer who has something like, I don't know, a PES++ repository where he is developing the code base for all of the tools that we're going to be talking about in this class. They have protections set up around those repositories because, it's a maintained code that has all sorts of, internal checks and processes. And so they want collaborators, but they also want to have some safeguards. So I don't push like a bug up into, PES++ IES, for example. So what most people do in terms of collaborating on something like PES++, and then I know that Mike and Jeremy and Rui, the other instructors in the Australian time zone, they've been building these GMDSI notebooks through this process of creating your own a fork, basically like forking that repo over into your own account, making your changes, and then sending those back through a pull request. And then they get to say yes or no, this is good or this is bad, or I can reject it. So I'm just going to walk through that process of forking and doing a pull request, which I would say is fairly intermediate to advanced GitHub. But once you figure this out, then anybody on this call who has any kind of ideas about how to improve Pest++ or any number of open source Git hosted programs can start doing that. So okay, sorry, I probably clicked on that without showing you guys. So you can go to this, and this is how we actually clone it to our own desktop. Mike showed, I think he was using SSH keys, but you can also use just HTTPS or HTTPS. But then above that, you'll see you can fork your own copy of Mike Feenan's Reimagined Adventure. And so I'm going to click that. It brings me to this page. And it says, okay, this is available. You don't already have a repository in your own account that's called Reimagined Adventure, which not surprising. And then, here's another option right here to just say, I only want to copy the main branch. Maybe Mike has a couple different develop or testing branches, and I only want the main sort of, released version of this. So that looks good. I'm going into my account, create that fork. So now I have my own fork that I can do, whatever development I want to it. And, I don't necessarily have to send that back to Mike's version ever, but let's say I'm a good open source citizen, then I'm going to do that. So I'm going to go through the same process now, but remember it says it's forked from, but it is in my own account. So I'm going to copy that, check that it's actually K Markovich instead of Mike's, and then just do a git clone. So let's go into that directory, reimagined. And here we are. We have that README file, and then we have Mike's Freyberg pest setup files. So let's say I think that he could improve upon that modeling fancy model file.dat. So I'm just going to look at it and say, oh, well, this is not just a file. This is more than a file. Just, one way to look at it. So I've made that change, and now I'm going to push that. And this is again to my own repository, and I'll show you guys how you would then take it to the next step to actually submit a pull request for that. So do git status like what Mike was showing, and you can see, oh, look, it looks like I've modified that one fancy model file right here. So that's been changed, but it hasn't been staged for commit yet. So that means I have to add that here. And now we'll do a git status again. And git status is your friend. When in doubt, always type git status. Make sure you're on the right branch. Make sure you're not, pushing have the wrong files staged, things like that. So now it shows that I have modified that fancy model file. And I am going to do the same thing, add a commit message, wordsmithed the file. And now git status again. Looks like I'm ahead of the origin main by one commit, but I still need to push that then to that repository. So I'm going to git push and make sure I'm pushing it to that main origin there. And now, oh, I forgot to git pull. That was my one misstep. Normally, when you're doing this, you always, before you push, you always want to pull first, because then you might have a merge conflict, which is nothing to be afraid of. So it looks like I'm up to date with the origin. And so now I can go back to the repository here, do the same thing Mike did. Let's go in here and check out that it's more than a file. It's not just a file. So that looks good. So great. Now I can go to this contribute button right here and open a pull request. So this is going to, send this to Mike and say, what do you think about this wording of this one file? So I wordsmith the file. I think it sounds better. And then we are going to create that pull request here. So then I can pass it back to Mike, and he's the keeper of the repository or the code base, and he's going to be able to say, no, I don't think that sounds better, and reject it, or he can decide to pull those changes into his repository. And so this is kind of a more formal way to collaborate and interact with on GitHub. But just to be clear, with a lot of these modeling projects, let me invite him into. You often are just both pushing and pulling to the same repository, and you don't have to do a pull request each time. But we thought we would show you guys this in case you did want to eventually become a contributor to PES++ or PyEMU or FlowPy. So I'll pass it back to you, Mike.
Great. Oh yeah, there's a question, are you not pushing to Mike's repo? No, she was not. And the reason that that's the case is because, sorry, let me turn a little bit. The reason that that's the case is because of this idea of making a fork. And that's what's really cool about it. So when you make a fork, you're basically working on your own version of the code. So you can, with open source software, you could make improvements that you never share back. Ideally, as a kind of a good citizen, you would, but you don't necessarily have to ever even push those back. But ideally, and this is why it's called a pull request and not just pushing to the main repository. In this case, Katie made this very valuable change to my model file, and now if I go back to the main repository, I can see that there's this pull request that's been made, and if I click on the title here, I'll be able to see that this exists, and I can even go in and look at the changes here and review line by line what changes were made, which is super powerful, right? So presumably, I can go through and kind of review these and decide, do I accept these? Is this a good thing or not? But say that I do, then I can just go here and say merge the pull request. And I can even make a comment like, thanks, that's way better. Right, and confirm the merge. And then now it is included. And just to as one final piece of illustration here, if I pull, I'm going to see that there were changes made. And it even tells me very abbreviatedly, like which file was changed, and there was a little bit of adding and subtracting. And if I look at that file, it's now in the state, this is more than a file. It's now in the state of that Katie's changes were made. So again, super whirlwind, but the idea here is we've all got a definitive version of things. We can have our own working copy where we can experiment and hopefully make useful changes. But then the kind of the owners of that repository are the final word on what gets reincorporated back into the main project. And I'll just say that this is a super powerful and complicated thing. And this is like my favorite cartoon about this. So this person is explaining to someone else, like, oh, this is good. It tracks collaborative work through this beautiful distributed graph theory tree model, right? And someone says, cool, how do we use it? Yeah, like no idea. Just memorize these few commands, type them to sync things up. And if it doesn't work, just delete it and start over with a new copy. And which sounds a little bit harsh, but we've all done it. We all continue to do it sometimes. And the reason is because there is this definitive version that is available to you at GitHub or wherever you're hosting it. You have the ability to just sort of like, you'll lose your local changes, but if you get things out of sync, you can kind of just bring it back down. And if that's a model or a modeling project, you've got hopefully all of the general state of the model, except for maybe a couple changes you're making lately. This is very, very powerful for working on teams. So working with groups of people. And finally, I probably some people noticed, but I found a couple, when I was first learning how to use Git, I found a couple really valuable videos, tutorials that kind of walked through a lot of this at a much slower pace. So I posted a couple links that may be of use. And this is basically the standard used in software development. So if you Google around or end up at a place like Stack Overflow or other forums, you'll find answers to almost any question you ask. So There is a limit when you're using model files, however, there is a limit to what Git will happily let you track basically any file you want, any size file that you want, but GitHub, since they're using cloud resources, has a limit. And that limit is you'll get a warning if it's more than 50 megabytes, and it will not accept it if it's more than 100. And so there are a few ways to handle this. Some things could be as simple as zipping up text files if you need to compress them, or breaking files into multiple files. Like, for example, if you're using ModFlow or other models that allow you to have properties, say, for different layers or different times in external files, then each of those files will not be quite as big. So there's some strategies to this, or maybe on some projects, there's some data that's just too big to share this way, and you have to find another way. But for most of the workflow, this works really great.
Yeah,
cool.
And I just wanted to add that it doesn't have to be command line. I know that there's at least 2 GUIs, GitHub Desktop and Git Kraken, that people can use that I think for a lot of people, seeing kind of visually, especially if you're working with something that has multiple branches and you're going to be merging it back into the main, these GUIs have really nice diagrams for where you are exactly on this Git tree. And then, yeah, what Mike was saying about the large file thing, using a git ignore, which was one of the files that he had hidden in his directory, is really useful for that. So you can, we don't have to go into it, but the resources will go into how you can set up a git ignore, and it's basically just helps to protect you so you don't add, say, a cell by cell output file from ModFlow or something. And then generally, though, I think what I personally do for this is, you just be very careful. Rarely, if ever, do I just do git add and then add an entire repo or folder, because you never know. Every now and again, there's like a shapefile that comes in there or a DBF for a shapefile that's like massive, and it will just sneak in and then jam you up for the next hour. So those are a couple strategies that you have.
Yeah, definitely. This is an example of what the git ignore file looks like, and you just basically can say folder names or extensions or various different ways to identify files. So yeah, so definitely Thanks. Very helpful. Cool. All right. So you may wonder what this has to do with with groundwater modeling and parameter estimation uncertainty. We just wanted to give the background for how these things are organized. And now we'll just take a quick overview of the actual notebooks that are in the repository that you all have access to. And so if you're at that main folder, GMDSI notebooks, you're going to spend most of your time in this place called tutorials. And we've got a bunch of notebooks, Jupyter notebooks, that are all in sequence. And they really fall into 3 parts. Part 0 is basically like really basic background and kind of specific to certain topics, not necessarily to a certain model. And so I encourage people to go through this introduction to regression. This is just sort of the general idea of like how taking data and changing parameters in a model, like how we can systematically use statistical theory to do this in a formal way, which is really at the heart of what PEST and PEST++ are doing. The exact algorithms that we use differ, but there's some good concepts, I think, in there that are worth exploring. And then a couple special topics that'll come up, like geostatistics, Bayes we're going to talk about a little bit today, but there's some more information here. So these really, I would think of as reference, with the exception of the regression, which I would encourage everyone to look at. These other ones, you can kind of, if terms come up that seem like this would be a good place to look, it's a good place to go to kind of track them down. And then part 1 is mostly material that we developed in quite a while ago, like before the iterative ensemble smoother was around. And so it starts kind of with the simplest way. You can see that the first notebook in here is called trial and error. And so we'll use this example model that Katie's going to introduce in a few minutes called the Freiberg model. and start as simple as possible, just trial and error. How can we evaluate whether we can get a better set of parameters for that model? And then starts to add complexity bit by bit, with quite a bit of discussion about how the algorithms work along the way. So this is good, but definitely not. I would say this is not designed to be sort of a workflow that you might use now. It's really in the context of these specific topics. Part 2 is where we really start like hitting the road, and this is really pretty close to, I would say, the way that we often run projects now. This kind of sequence. We're going to set up the model to work with pest. We're going to have to do some work with observations and weights. I spend probably 70% of my projects in prior Monte Carlo, kind of revisiting prior Monte Carlo a lot, and we'll talk more about that. And then there are a couple of choices to make here, whether you use the Gauss-Levenberg-Marquardt algorithm or not. Often people end up skipping straight to the iterative ensemble smoother these days. And then these management optimization techniques are at the end. So this is really a little bit closer to a workflow. And this is what we're going to be having you, your assignments are going to be from week to week are going to be through this sequence of notebooks. But just know that these other ones are available to look back at and can be quite useful for background. And finally, one of the things, like if you're going to use these tools with Python, using PyEMU is really this Python interface into the PEST++ framework of tools. It's super powerful, but it's also under really active development, and it changes a lot, which is okay. But the challenge with that is, if you're working on a team, it's very likely that you want to make sure that all members of the team are using the exact same version of that tool. Similarly, there's a tool for those of you using ModFlow called FlowPy. It's a Python interface into the ModFlow family of codes, and that also is under active development. And things can change. Something as simple as a naming convention for a file could change. But then if you have a scripted workflow that's expecting a certain file name and it changes underneath, things can break. And so the way that we've handled this is making sure that everybody is using the same set of tools. And so if you look in this dependencies folder, there's a whole folder of FlowPy and PyEMU. And there's a clever way to that if you ran through the setup, well, you all did, because you all got the secret code to join us here. And so going through that sequence, one of the things that was done was making a dynamic link to these codes in your Python environment, in your Conda environment. So what that means is if you were to change a file in here, like some of the code, your environment will be using this version, not one that you installed from the internet. But the great thing is, this being a Git repository, if you're working with collaborators, they'll be versioning those same files. And every time that anybody uses that environment and uses this repository, they'll be using the same version of FlowPy, PyEMU, or anything else you wanted to put in here as well. So it's useful in this case, so that everybody should be getting the same behavior in the notebooks as you run them. Otherwise, somebody might have had an old version of PyEMU, or somebody might pull a new one next week and it might change something. So it's really important when you're running these notebooks to be in the environment that you set up for this class, and then recognize that you're using these particular versions of the codes. Similarly, we have all of the binaries, things like PEST++, has several executables that we'll use. This is the Windows version. So Windows, Mac, and Linux, these are also the exact versions of those tools that you're going to be using when you run the notebooks. So the idea is that everybody should be in sync with these tools. Cool. So I mentioned that really all of these notebooks, part 1 and part 2, are using an example model called the Freiberg model. And so I'll turn it back to Katie to introduce how that model works.
Yeah, great. Just as a time check, Mike, we've got probably have. I'm going to go through the Freiburg maybe in Bayes a little bit quickly so we can get to the good stuff at the end. I'm going to go back to sharing my screen. So I'm in the GMDSI notebooks repository here. And first thing I'm going to do is activate my environment that I built from the YAML file. And there we are, I'm there. And I will launch Jupyter Notebook. So that brings up this here. So we are first going to go into the tutorials file. And then these are, yeah, this is what Mike was just walking everybody through, but we have an intro to Freiburg model here. So the Freiburg model is named after David Freiberg. He was a Stanford hydrology professor who had a pretty elegant exercise that he had his students go through. This is back in 1988, so this is pre-PEST, obviously pre-PEST++, where he basically grouped them up in pairs. He gave them a very simple box model, gave them the water levels that were perfectly known for a number of wells, gave them the bedrock elevation, the surface elevation, lateral, basically everything you would need to know about this model, boundary conditions, well pumping rates, and then a uniform hydraulic conductivity field. And he basically said, you know, go forth and manually calibrate this to minimize your misfit between modeled and measured water levels in those wells. What he didn't tell them was that the forecast of interest of this model was heads if the river channel was lined. So if you reduce the conductance of the river quite a lot, which was inspired by what was happening all over the place in Southern California at the time or prior to that. And it's a really elegant paper because it basically demonstrated, you know, in a quite simple but effective way that you know, the best fit does not necessarily yield the best prediction. So if that were the case, you know, the root mean square error of the prediction would follow a one-to-one line with the root mean square error of those observed heads, right? So the largest error in heads would lead to the largest error in predictions. But you can see by these crosses here that that was not at all the case. In fact, the lowest root mean square error that one pair of the students made actually led to the highest prediction error. And this was a case where they basically were manually calibrating or tuning cell by cell the K to match heads and, you know, where they have well observations. And conversely, one of the better prediction root mean square errors had actually the worst calibration. And these folks chose to kind of take a zoned approach. So there's a couple takeaways here that I think are really relevant to, you know, everything related to what we're doing with PEST++ and using these, you know, probabilistic and highly parameterized approaches, which is that, you know, first, the goal of building a model is rarely to actually estimate the parameter itself or to say, look, I built a good model. The goal is usually a prediction. The second one is to be wary of overfitting because our observations are not just pure information. They often have what we call noise, which could be anything from, you know, a process that's affecting your water level that is not present in your model. It could be a structural error, all sorts of things like that. And so if you overfit to match that head perfectly, you might be overfitting the wrong parameter to do that, which is going to then compromise your prediction. They also pointed out issues with non-uniqueness, and we have a Jupyter notebook actually that kind of walks through how if you only have water level measurements, the combination or ratio of recharge and hydraulic conductivity leads to, you know, numerous good fits to the water level observations. And so it's a good paper to read through definitely in starting this class. And then Randy Hunt actually had a follow-up paper using the tools that are available to us right now. And he also found some really salient results from it. So I think it's I found it to have a profound impact. But so I'm just going to walk through the model just so that we all are familiar with it. And this is something that is going to be important as we're building up the PEST from interface and starting to actually do some uncertainty analysis or iterative ensemble smoother work. So first things first, we are going to import our packages that we need. We're going to set some paths. So we're setting a path to the model files here and then to the Freiberg model files. And then we're going to load and run the simulation here. And so with any luck, it has run. And so one important thing that happened between the time of David Freiberg and now is Jeremy White and others took that Freiberg model, converted it to ModFlow 6, converted it from a steady state single stress period model to a 25 stress period model that reflects, an initial steady state stress period, but then a predictive year or historical calibration year, and then a 1 year predictive year. So there's observation data available for that first year of the simulation, but then the second year is the predictive period. And he converted the river package to SFR. So we'll just plot up. Oh, maybe I didn't actually run that. My bad. There you go. This error was just saying that I actually hadn't loaded groundwater, what we named the model. So now we have, it's a 1-layer model. There's 40 rows, 20 columns, and then we're going to plot up the boundary conditions. So you can see this is that rectangular model. We've got some outcrop areas here in black. These are no flow. These are all of the pumping wells for which we also had observation data for. The SFR package, the river going right through it. And then the outflows of the model are this general head boundary condition. So major inflows are recharge and surface water leakage. Major outflows are pumped flows, groundwater flow to the river, and then flow through the general head boundary condition. And then I'm just going to walk through some of the properties. So again, everybody started in that class, and then us as well as we work through this with just a uniform K field here. And then we have, perfectly known geometry of the aquifer system. So this is the bottom or the contact with the aquifer sediments in the bedrock. And then this is the surface elevation here. So I already mentioned there's 25 stress periods. It's a 1 steady state and 24 transient. And then the first 12 transient stress periods are the historical, second 12 are the future condition. We have some observation data shown here. So this is the stream flow gauge observation data, and this is for each of those wells. We have transient water level information here. So that's from that observed data CSV file that we're loading in and printing out here. And these are the model simulated counterparts. So we have the ModFlow 6 file set up so that the SFR package is printing out stream flows at our specified locations and heads information for each of these wells. So we can actually read that SFR CSV file right here. And I know I'm going through this quite quickly, but we'll record it and make this available. So we can look at that SFR CSV, and we're actually recording a number of things, not just that gauged outlet, but actually we've split up the river into 2 sections. One is the headwater. So this is the surface water, groundwater exchange flux for the headwater reach. And then the same goes for the tailwater. And so this can either be negative, which is groundwater to the stream, or positive, stream to groundwater, following the ModFlow convention of negative means out of the model and positive always means in. And we can look at the simulated versus observed for that gauged outlet flow. So this is the model simulated, this orange line, and then this is the measured flow. And this, you'll notice this flow actually has quite a lot more noise to it, a lot more variation. And this data set was generated by using a higher discretization, same Freiberg model. So more rows, more columns, more layers, and using a daily time step daily stress period rather than monthly. And so we can walk through then that same heads CSV output file that we get and plot the measured versus observed here, just to kind of get a sense of where we're at in terms of starting out this process. And, you can look at this, and so this is that 2-year period. We have cyclic recharge, and then there's also a signal of pumping, because those pumping wells are active throughout the whole simulation. And right off the bat, right, it matches the kind of fluctuations, but obviously there's an offset here. So, I think we all can empathize with being in this position when you're starting out on a modeling project. But I look at that and be like, hey, we're doing okay. And this is just a plot of the simulated heads where you can see the impact of those pumping wells drawing down. But the most important part of this Freiberg is what we're forecasting, because this is like ultimately what we're after with this process is, our forecasts, the uncertainty around those forecasts, improving those, maybe doing some optimization around them. And so the forecast that we care about in Freiberg is what I was calling those aggregated surface water groundwater exchanges for the headwater and tailwater reaches during stress period 22, which is into that near the end of that predictive period. Groundwater level at a location, I believe it's like up here. So in a location where we have not assimilated any information for at stress period 22. And then they also added particle tracking to the Freiberg model as a way to kind of test it even further, because particle tracking adds a whole new layer of complexity and difficulties in prediction, because we're adding in porosity and travel times into the mix. So these were, selected to represent a range of modeling outputs that are informed by data in varying degrees. So that is a whirlwind tour of the Freiberg model. And I think next, am I going over Bayes, Mike? Yep, I am.
Yeah, we did get a little bit behind, so I'm thinking, but since this will be recorded, if people need to drop off at the top of the hour, that's cool, but maybe we'll go 5 or 10 minutes. A little bit over, just to make sure we get through what we hoped. So
yeah. And all of this is available and really annotated in the notebooks themselves. So this can be a very simple, quick one. But basically, the underlying statistical philosophy of the PEST universe and PyEmu universe is Bayesian rather than frequentist. And it's the idea that we have our prior understanding, and then we have what we learned from the data through that inverse history matching process, which is the likelihood, which helps us arrive at our posterior. And that can be with respect to our predictions, our input parameters. For all of these things, we have our prior, our likelihood, which is what we gain from the data, and posterior. And with this, it's a really powerful, so this is just, again, I'm going to go through the packages here. This is just kind of a demonstration of that process of Bayesian updating, basically, where we have our distribution for, let's say, hydraulic conductivity, our prior estimate. We're saying we think it's starting at 10 as the mean or expected value, but that we have quite a lot of uncertainty that, a large space where that value could potentially occupy. So, obviously we're not going down to -10 hydraulic conductivity. Let's just call this mega log space. And then it can go up to as high as 30 here. And then we have our, we take our observations and we go through our history matching process. And let's say we have a lot of data and it's very informative, right? So we have a much more narrow distribution here for that likelihood. And our posterior then is going to be pulled closer to where we have the most information or confidence, basically. So it looks quite a lot like that likelihood, right? But we have a nice little interactive widget here in this notebook where you can kind of play around with this idea of, confidence in, or, our knowledge, which can come from field information, can come from expert knowledge, can come from literature data of our prior, which I think is a really important and perhaps maybe under emphasized part of this process, because everyone wants to see those history matching fits, right, and get to the posterior really fast. But building a really solid prior, I think, is really, really valuable. So let's say we have, well, this would be a super uninformative prior. Like it can vary anything from -20 to 40, right? Then we see that our posterior is essentially a mirror image of that likelihood. But let's say we have a much more confident prior, and let's move our mean a little bit further away between our likelihood and our prior. And now we're kind of splitting the difference with that posterior, but it's sort of, it's being pulled closer to where we have the most, confidence or information, basically. So I think this is a really nice thing to play around with on your own time if you want to get comfortable with this idea of, maybe you have a really, really good prior and not that great of data, and what can you expect to see in terms of that history matching and parameter upgrade process. Okay, I think that I can pass that back to you now, Mike, for the pest from start or setup.
Boom. Yeah. All right. So, so as Katie said, like basically the framework here is this Bayesian idea where we're going to be using information that we like, observation information that we have, and we want to somehow inform the model of that and update parameters. So we start with some conceptualization of these parameters. We update the likelihood the likelihood function is the process of looking at the misfit between model outputs and those observations, updating those prior to be the posterior distribution. And so this is done in a way that sometimes people have called automatic parameter estimation, which I don't like because it's really not automatic. But what it really means is that there's a few components that we have. We have this set of observations and we have our model, but we need some kind of an algorithm, and we'll talk more about what that algorithm is, to take the information from the observations and use it systematically to update the parameters. And to do this, basically the algorithm needs to be able to somehow write input into the model with a new set of parameters, run the model, evaluate the outputs, and then make a decision about a new candidate set of parameters. And so conceptually, this is just sort of a flowchart to look at this. If we have a forward run, it's fed some kind of input files and it writes output files, right? So we can take some subset of those inputs, say like hydraulic conductivity in a file. We can define that as a parameter that we want to estimate. And there's a control file that PEST uses, which is sort of the orchestrator of this whole process. So the very first thing you do is really define a parameter that you want to estimate. And then there's a special kind of file called a template file that looks almost exactly like an input file for a model, except where there's a numerical value for the input file, it's replaced by this named parameter. And then these little tildes are some kind of a delimiter. Ideally, the tilde, well, it has to be that the tilde is not used for any other purpose in the model. So PEST is able to look for pairs of these tildes, and whatever its current value for hydraulic conductivity is, it will replace this whole string, the tilde, the name, and the other tilde, with a current numerical value, and then write a version of the input file. And so again, every file, every parameter that you want to estimate has to be defined in this control file. And then you make this connection. You tell PEST in the control file also what is the forward run, what is the actual model run. So that might look something like this. It writes output, and then we need a way to read that output back out and define observation data. So again, these have names like H1, H2, H3 are meant to be heads in this case. And we provide the PEST control file with actual observed values for these. And this mechanism of using an instruction file with the output reads the current value from a specific model run and provides it back to PEST in memory to make the connection between, basically calculate the misfit. How off are we between when comparing modeled outputs to the observations, maybe, and then when it then comes up with a new set of parameters, and then this whole cycle just continues. So to do this, the main stipulations are that PEST needs to use text files. It needs to write a text file for the input. It needs to read a text file or an ASCII file for the output. And so if there's any, like if their model is putting out binary or takes binary as input, you might have to write a little helper function in Python, or it can be really in any language that takes the text input, converts it to whatever the model needs, and then same on the other side. And so this forward model run is usually not as simple as just run modflow 6 or run feeflow or something. There's often some pre-processing, there's running the model, and then some post-processing to get things into a format that's easy for Pest to read. But this is the main cycle of what we need. And on the input side, we need to define which parameters we want to estimate. They all need starting values, and they all need credible or reasonable bounds over which will allow them to vary. The algorithm can allow them to vary. That's on the input side. And then on the output side, we simply need model observations from the field, and then co-located model outputs, co-located both in space and in time, so that we can make a meaningful comparison between the two. We're going to talk next week about what kind of the ramifications of the choices about observation values, and certainly something called weights, because PEST is using a single metric of misfit. It's called the objective function, and it's basically a sum of all of the residuals, all the differences, individual differences between modeled output and observation, summed, but also applied with a weight. And we'll talk again about what the ramifications of that next week. But it takes all of that information and aggregates it into a single metric. And the whole algorithm behind PEST and PEST++ are various ways to try to minimize that objective function. And in a sense, that's trying to say, make the observations as close, the modeled outputs as close to the observations as possible, but within reason. And that reason is a big part of why humans are still in the loop of this whole process. There are also, we can assign, the one thing I'll say about weights right now is that we can assign 0 weight to certain observations. For example, in ModFlow, people often look at mass balance as a diagnostic of quality of the model. We can report that with 0 weight. That means it won't play any role in the parameter estimation, but it also means every time we run the model, we can look at that diagnostic, and that's super valuable. Other things like, did the model converge or not, or even model runtime, or other things like that. So I'll just point you that this notebook is in the part 1 series, and it's called Pest Setup. And it's a long notebook, but it really goes through a lot of the details of how all of these things work, what are the ways to set up template and instruction files. And you can do this by hand, basically. You can do this all like manually, just using a text editor. You can also use a GUI. A lot of popular GUIs for models have facilities to make some of this. But the way that we're often using it, and the way we're going to do it in this class, is using a really powerful PyEmu function called PestFrom. And so Katie is now going to demonstrate how that works.
Yep, sounds good. All right. So I'm going to go back to the reimagined adventure repository and live code this. Take the wheel. See how that goes.
Live coding always works perfectly.
Yeah, exactly. There's nothing could go wrong at all. So I'm gonna, let's see, go to where I have the reimagined repository. And actually, I will just copy over the model files from the repository for the GMDSI notebook. So the monthly model files, 1-layer folder that you all have probably seen. And I'm just going to drop it in. There's probably a better way to do this with command line, but here we are. So I've added those files. So the first thing I want to do, because these are our base files, and we don't really want to touch those. We want to work in a way in which we have, our set of files that we keep as the originals, and then any kind of updates that we make from there, we're going to create a new folder with some kind of informative name and go from there. And that way, we're making this fully reproducible, and we're not having to track things like model outputs and stuff like that. So Git add, and I'm going to add this whole folder because I know that there's nothing super large in there because it came from a different repository. Commit model files here and do that really quick just so it's up there now. And so we have that, and I'm going to do this from a Jupyter notebook. Did I spell that wrong? Oh, I didn't activate the environment. This is awesome. So this should open up a whole new notebook here. Let's see, new notebook. Let's go with that. So we have just a fresh blank notebook right here that's in my fork of Mike's reimagined adventure and pop repository. So, some first things that we want to do is import packages that we are going to need. So that includes OS and PyEMU. I think that's probably everything we need. Let me run it. Looks like we're okay. New kernel. Do you know the quick key for adding a new?
For a new cell?
Sorry? Yeah, new cell. Yeah, not kernel.
You can hit escape and then B.
Escape B? Oh, sweet. Thank you. Great. Learned something new today. So let's first set a path to our model files right now. So let's just say, call that model WS equals, we always want to use OS path join here because we are frequently using in different operating systems. And so this just helps with the / nonsense that will happen. And let me just copy that name because it should be in the same. This is our base model files here. Looks like that loaded okay. And then I'm going to just run it really quick. So escape and B. Awesome. So there's this handy function in PyEMU OS utils. So it's operating system utilities. And I believe I could just do run here. And then I'm going to call modflow 6. And then current working directory is going to be model WS here. This is probably going to fail because I don't think I have the I don't have the executable in here. So I'm going to do the cheater version and just add it. But normally in our workflows, we would have what Mike was talking about, where we have our folder of our executables that has always been copied into our model folders to keep everybody using the same version. But in interest of time, I'm just going to copy that over. So I need modflow 6 and I'm going to need pest eventually. And then add that to this guy. So now this one should run. There we go. Cool. So we've got first step done. Get model files in there that are running. And let's see, I should do a new, here we go. So now is where we get to the really, really powerful stuff. So I am going to build using PyEMU pest from, or instantiate what we call a pest container. So it's basically just like a container where we add everything that we need in a pest workflow. So what Mike was just going through, we need to add our model in our model files, need to add all of our parameters and all of our observations. And those are kind of the primary components of the pest control file and what we need to be able to run things. And it obviously goes much deeper and much broader from there, but that is the, the simplest, most boiled down form of, a pest ++ instance. So the first thing of here, let me just do this first to make sure. Oh, pyemu.pest. Pest from. Might have to actually look this one up, Mike.
It's utils.
Oh,
That's right.
Thank you. There we go. See, coding from scratch. So this just tells us what we actually need to instantiate, which a lot of these things are default arguments and we don't really have to mess with. But the things that we definitely need always are that original directory that has those model files in it, that new directory or template file that we're going to build in this. So basically we're going to copy those model files over, and this is going to be the directory that pest puts everything else into, including our template files, our instruction files, everything. So those are two arguments that you definitely always need to be specifying. And then the rest of these are, do you want to keep it zero-based? Do we want to give it a start date time and things like that? And remove existing means, are we going to delete that template file if it already exists in your directory? So I'm going to say original, or I'll just call it model WS, and then we're going to call this new one template. And here we go. We have built our, instantiated our pest container here. So we have that. What do we do with it? The first thing I like to do is to start adding some parameters. So let's see, if we take a look at our model files here, it's a classic, it's the Freiberg model. So we talked a lot about hydraulic conductivity. Why don't we add parameters for hydraulic conductivity right here?
Hey, Katie, you're going to have to, yeah,
that's right.
You got it.
We have to actually create, oh, it already exists probably. I need to replace existing. Nice. There we go. Oh, did I misspell that? Right, folks, this is science in action. Remove, did I type replace existing instead? React was much smoother.
Nah, you got it. That was it.
Okay, cool.
Right.
So now we have our actual container, this PF. This is what we need to actually start to add things to. Otherwise, we just instantiated a pest container into the ether and it will never come back to us. So to add parameters here, I'm going to do the same thing just to show you guys. There's a lot of arguments that we can specify here that they go into it in detail in the notebooks. Like what parameter type, what is the kind of, what is the uncertainty range that our upper and lower bounds reflect, all sorts of things here. But we are adding a very simple array type input file. So the file name is Freiberg 6. I'm just going to copy paste out of laziness. And then the parameter type is just grid based. Let's call that. Why not? And this should work. So now we have, I didn't pass any kind of transform, so it's going to assume it's a log, and then it's adding those parameters. And this is just using all of those default arguments here. And so now we have, and this would be in the pest control file under the parameter data section. So we have our name, the value, the location, the group name. Eventually it'll have the upper and lower bounds, things like that. So that's our very simple, there should be one parameter for every single cell of the K field currently in this model. And then now let's add some observations. So we looked at those heads and SFR output files. Let me see if I can find them again, that the model is writing with every simulation here. So this is all of the time outputs of the model. And then these are all of those locations that we are recording heads information from. So I'm going to add, just like with observation of the parameters, I'm just going to quickly show that. Again, it's file name. Importantly, with the observations, we want to be able to specify what the index columns are and what columns we actually want pests to grab the values for, the modeled values, to be able to then compare to our observed values. So these are two important arguments to specify to tell it in here. So let's say I only, if I want all of these, I would give time as the index value, and then I would want to say use the rest of these columns. But for simplicity, again, I'm just going to say, let's use this one column and set that up. So the file is heads.csv, and then index calls, and these can be an integer for the column number, or it can be the actual column name here. And then use calls, right? Yeah, use calls is this guy. Let's see if that works. Got an unexpected keyword argument. Something I did wrong here. Index calls, missing an S. Classic. There we go.
Unforgiving.
Unforgiving. I'm only doing this for your learning a bit. This is, I would never make a mistake otherwise. So we have now added all of the observations. So we have observation name, which is basically that TR groundwater, and this is the layer row column. And then Pest has intelligently added the time index to each of the names in time. So we have that value as observation value, we have a weight, and then we have an observation group name. This would be in the pest control file observation data section, for those that are familiar with pest control file. So now we have parameters, we have observations. I think we have enough to actually run pest here. So let's see, PyMU, utils, and now we are going to run. Mike, do I need to write the files first? Or I can just run it as it is, right?
No, you still gotta build the files and then.
Oh, that's right. PF build pest. Thank you.
Mm-hmm.
Let's see. So here's where we build pests, and this is where we have a really nice option now, where this is going to be the name of our file. So let's say I want this to be Freiburg.pest. I would give that for that file name. And then version 1 is the old school style of pest input of the pest control file. So it's everything in the pest control file. You'll find that in this highly parameterized space that gets really unwieldy really fast. So version 2 is really nice in that it takes a more distributed approach where it writes out just one CSV file, say for the parameter data and the observation data, that then is linked to in that pest control file. So I'm going to give it file name is, we want to make sure it's in the template directory. I think it's pfnewd that we can do here. And version there, Freiburg.pest. And version 2 is what we're going to go with here. And we have built it. So we have 800 adjustable parameters here and 25 observations. So we can look at where that built in this template directory here, and it builds out what I was talking about. This is that control file. Instead of it being a super unwieldy thing, we now just have, our control file parameters here, and then our CSV files that contain our observation data, our parameter data, that forward run line, and then the template and instruction file information. And I'm just going to pop open forwardrun.py as well, just so people can see. This is what is actually running the model each time, but like Mike was saying, it's not just a model run. It's often, many pre-processing and many post-processing functions, and we'll dig into that later on in the class. But right now, all it's doing is applying those multiplier parameters and then running. Oh, I actually didn't even add that. That's an important thing. I didn't add that model forward run call. So it's just going to apply the multiplier parameters and then exit and say success. So that's not actually what we want to do. So I would go, let's see, up here and add that before we build pest. It's pf mod, like something like this. I'd have to Google it. I don't think I have it from memory.
It's CMDs.
Thanks.
Mm-hmm.
Nice. And then MF6, I believe.
You got to append it too. It's like .append because it's already a list.
Awesome. Thanks, Mike.
Mm-hmm.
And then let's rebuild it and see if we fixed that. And that for run file. There it is. There's our run line. That's what we want to see. Awesome. Cool. So now we have everything and we actually can run it and see if pest is working. I believe, let's see what we set for our enupt max variable, which is basically telling us, you know, how many pest upgrade iterations we want to run. It's set to 0. So we won't be running any. It's just going to run the control file parameters once. So it's going to run the model once with those values that are in the control file, and then it's going to exit and hopefully give us a fee. Let's see, escape B and go back to that handy OS utils run. And if you were using a Windows, you would want the exe here, but Macs and Linux don't need that. And then now we can use, let's just call it template here. All right. Oh, we got another error here.
You need the pest control file name too.
Oh, that's right. PS here. Thank you.
Just right there. Mm-hmm.
And if you're lucky, you have Mike, who's pair coding with you, running through this live. So yeah, we have now successfully run pest start to finish, and it looks like our fee is 0. So our work is done here. We're doing pretty good, I'd say. But actually, if you saw this, this would be, that would tell you something is very wrong. So I think that wraps up the live coding demo. And I think we can actually pause and take some questions now. Apologies for going over in time.
One quick note about why the fee is 0. If you use the pest from setup the way that Katie did, and if you have a special case where the observations in your observation file are actually derived from the model that you just ran, then you're basically saying the observation should be what the model's outputting, and the sum of squared residuals of that will be 0. So it's really a diagnostic. Another step later would be taking from here, putting in your actual field observation values.
Exactly.
So
yeah. Thanks, Mike. Yeah, thanks for pointing that out.
Yeah, no problem. Well, I think since we have gone over, I guess if there are any burning questions right now, we can hang out for a few minutes. But I will say first, in case people need to take off, thanks for bearing with us. It's our first time around here, and I hope it's going to be useful. And for next week, please take a look at the part 2 pest from setup pest notebook, which is oh, and sorry, yeah, I see there was a question about how to access the recording. We will send out an email with a location for that shortly, probably later today or tomorrow.
Yep.
Yeah, and then
they will also be posted to the GMDSI website. So if anybody has any issues accessing it, never fear. It'll be posted on Vimeo for everyone to take a look at.
Excellent. Yes. And so this is, part 2, pest from pest setup. So this is the notebook that you're going to want to work through for next week. So it's exactly what Katie just demonstrated, but with sort of a full suite or full complement of parameters and observations. So yeah, please take time to look through that, gather your questions, and yeah, again, we'll hang out for a couple minutes if there are questions. Otherwise, we'll see you all next week. And I believe we have to send out a new invite, right, Katie? It was only for today.
Yeah, exactly. Yeah.
Okay, so you'll get a new invite, and you'll get a link to the video recording as well.
Great. I think there was one hand up. Maybe he lowered it. Jack, do you still have a question?
No, I was wondering about that video recording, so Stan, thanks for addressing that.
Okay, cool. Looks like Salvador has a question. Do I need to unmute? Maybe.
You should be able. They should be able to. Salvador, you should be able to unmute yourself. I think.
Hopefully. Okay. Well, No questions. All right. Nice.
All right.
Well, yeah, I look forward to the next meeting, and it'll be a lot more like interactive discussion based, a lot less Mike and I just talking at you and me having demonstrating my coding errors. All right.
Awesome.
Well, thanks y'all.
everyone.
Have a good rest of your day.
Thank you.
Thank you. Bye.